All right, so we need some rules for product and quotient derivatives. Okay, so we want to be able to take the derivative of a product of two functions and then a derivative of the quotient of two functions. Now, unfortunately, these rules are not as nice as, say, the sum and difference, where you just split them apart and you can do them in either order and it doesn't matter. Not the case here. In particular, if we look at the product rule, if we want to take the derivative of the product of two functions f and g, okay, we can't just take the derivatives individually and then multiply the results. It's just not going to work. If you don't believe me, think about taking the derivative of x squared times x squared. Okay, if I did it individually, that would be 2x and 2x, so I'd get 4x squared. But we know that if we simplified what was inside, that's x to the fourth, and the answer is really 4x cubed. So this would not be right. So that's just not going to work. Okay, so instead we need the real rule here. And what it is, it's not too bad. It says basically you have to take the derivative of one at a time. So the derivative of f of x times g of x is the derivative of f of x times g of x as it is, plus f of x as it is, times the derivative of g of x. So in the first one, we're taking the derivative of f, but leaving g the same. In the second part, we're leaving f the same and taking the derivative of g. So that's how it works, and actually you could do this for bigger products. If you had three of them, you would get three terms where each time one of the functions is having its derivative taken, and the others are being held the same. Okay, so that's in the Leibniz notation here. Sometimes it's easier to remember from just the prime notation with this version. So fg prime, so that's the product fg with taking the derivative, is f prime g plus fg prime. Still the same idea. Take the derivative of one, multiply the other as it is, add that to hold one, take the derivative of the one that you didn't the first time. Okay, so let's go ahead and show this in some examples so we can get used to it. Okay, so we're going to do the derivative here of 2x plus 1 times x minus 3. We're going to do it as a product, and then I'll show you that what we're getting makes sense that it's true. All right, so what I'm going to do is I'm actually going to use a switch of notation. So I'm going to use the prime notation here because it'll be a little cleaner to look at. So I'm going to take the derivative of the first term, so 2x plus 1 prime, times the second as it is. So I'm not taking it, I'm just showing the derivative, not taking it yet. Plus the first one as it is, 2x plus 1, and then times the derivative of x minus 3. All right, so let's actually do those derivatives. Well, the derivative of 2x plus 1 is just the derivative of 2x, which is 2. The derivative plus 1 is 0, so it's just 2. And then I have times x minus 3 as it is. Plus, then I'm going to have 2x plus 1 as it is, and then the derivative of x minus 3, derivative of x is 1, and the derivative of minus 3 is 0, so I just get 1. Okay. So, now some of these steps you'll be able to do in your head in the future. I'm just showing it all out so that we understand how the formula is working here. Okay, so now I'm going to multiply this out. So I get 2x minus 6 plus 2x, so this is just 1 distributed, so it's still just 2x plus 1. And we end up with 4x minus 5. There's our derivative. Okay. Now, this happens to be one we can check if you're not buying this. If you're not believing that this is working, let's check by instead multiplying this out first. So if I FOILed that out, that would be 2x squared. Then I'd get a minus 6x plus 1x is a minus 5x. And then minus 3. And then if I did this as the derivative of a polynomial, I would get the derivative of 2x squared, bring the 2 down, so 4x, and the derivative of minus 5x is minus 5, and now you see the answers are the same. So now, while I could do that, and I might in a situation like this, because it was actually somewhat easier, I do need this product rule for more general situations, such as the next example. Okay, so the derivative of x sine x. Okay, so one of the most important things in your derivative taking is going to be to make sure that you notice the construction of the thing you're looking at. So whenever I get a problem like this, I want to look at that and say, what am I dealing with? And the first thing I should say is, that's a product of two functions of x. Okay, so that means I'm going to use the product rule, where that's one function and that's the other. So x is one and sine x is the other. So it would be the derivative of x times sine x as it is, plus x as it is times the derivative of sine x. Derivative of x is 1 times sine x as it is, plus x times the derivative of sine x is cosine x. So what do I get? I get sine x plus x cosine x. Okay, so that's how it worked. Now, of course, that one I needed the product rule. I couldn't do it another way, but I did get my answer. So this is just something you're going to have to practice, and you're going to have to do a bunch of problems as examples just to get used to taking the derivative of one, holding the other one the same, plus holding the first one the same, taking the derivative of the second. Okay, I should make a note here of, realize that before, remember when we were doing derivative of, say, 3 sine x. All right. Now, why didn't I use a product rule there? Well, in essence, I can, but I don't need to. I can always look at this as two functions, the constant function 3 times sine x. And imagine I did this. I would have the derivative of 3 times sine x as it is, plus 3 times the derivative of sine x. But the derivative of the constant here is going to give me 0, which is going to knock out that whole term. And then I'd get plus 3 cosine x, so I'd actually get 3 cosine x, which is what I get if I just instead treated this as a constant multiple, which is how I should do it. And then I would just get the same result directly. So when we have constants multiplying, while it is technically a function, I don't have to treat it as a product in the product rule sense. The key for the product rule is two functions that both explicitly involve the variable that we're taking the derivative with respect to. Okay, I could not have done that as a constant multiple here, but I could do it here. Okay, so that's the product rule.